Okay, so let's give this a try. I tried it out before, and it seemed to be pretty good. Okay. Okay. So why are we talking about Scala in this course, and why scalable software engineering for data science? So data science is a relatively recent term, having been coined within the past 10 years or so. Excuse me, almost a little bit less than 20 years, since about late 90s, introduced by a statistician, where he argued that statistics actually as a whole should be termed data science. And really, there's varying definitions, but it seeks to provide systems, methodologies, and procedures for deriving insight from data. And so it extends from the issue of sort of building algorithms that are scalable to large amounts of data, to how to leverage diverse data to most reliably make decisions or classify things or infer things, various types of predictive analytics, as we call it, to the design of the systems that host this data in a fashion that they'd be able to handle massive quantities of data, typical of so-called big data. And much of the drive at the moment towards data science as a field is surrounding this issue of big data. So I want to talk some about big data. Now, many of you have heard me speak about this at one point or another, and indeed we do quite a bit of work which helps convey some of these definitions in the context of health, particular. More generically, big data is sometimes defined, I think, poorly as data of such size, volume, variety, etc., that it's not possible to process it effectively using traditional architectures and approaches. It's too big and sort of unwieldy for us to work with our traditional data stores, things like relational databases, SQL in its traditional form, etc. But I think that's a fairly poor definition, because what we can do in those architectures is changing over time. It's not a natural kind. It's a kind of unnatural kind from a philosophical perspective. And I think so that definition points you to an unnatural sort of definition. I think it's undeniable, though, that big data does refer to a quite distinctive type of data, often drawn from electronic sources, where we we're distinguished by the so-called 4 V's. And Google introduced this term, and I'm rather fond of it. Sometimes you'll hear fifth V as well. Basically, it's characterized by lots of evidence, volume, high velocity. What I mean by that is it comes in very quickly. It's high temporal resolution. We might have many samples over the course of an hour, much less a day. In some cases, we have many samples a second coming in. You think about data from continuous accelerometry. But beyond the volume, which is kind of the focus of big, and the velocity, there's also variety. And this is really important for understanding performance issues, and particularly the barriers to traditional techniques. We typically, to make sense of this data, to render it into valuable insights, we are typically grappling with a lot of different types of data being collected at the same points in time, and often for the same customer, the same patient, the same individual in the population. So this data is made to consist, say, for a given person. Let's consider it someone being monitored by Ethica data, part of the IEPI project, and we think about the data collected from them. We not only have their accelerometry over time, we also have their GPS over time, and we have gyroscope. We have information on whether the screen is on and off. We have surveys that they may have responded to or not. We have information related to their social patterns through Bluetooth, and a variety of other types of information. all this on one person over time. And that information, to yield the best value, it has to be cross-linked. And even particular items from within that, like accelerometry, it often consists of several data items. X, Y, Z, sort of axes of the accelerometer. Or for GPS, you folks know as well as I do, for many of you, we have GPS speed and GPS accuracy and the actual GPS measurements in terms of latitude, longitude, etc. Now, why is this significant? Well, it turns out that a very expensive thing on a lot of traditional database systems is it's associated with joining data from different tables. It has to do a lot of work to do that. And you can speed it up with indexing and techniques, but fundamentally it's an expensive operation. So this variety really matters in terms of performance with traditional systems. Finally, and we're not going to be talking about it here much, although I certainly talked a lot about it at the IEPI bootcamp, is this issue of veracity. The data tends to often be more accurate or more precise than traditional data sources. So these are some examples of big data, and there's many of these that we specialize in our group, as you know. Consumer electronic devices, sensors, from smartphones, from watches, the sort of thing that Amin has done very fruitfully with the Empatica smartwatch, or that Michael Long did, that Narges has been working with. These are sort of consumer electronic devices. But beyond that, we also have the questionnaire responses from Ethica, right, that are coming in. Beyond that, some of our projects involve other sorts, like this browsing behavior. We have that for the participants in the Harvard study. We have cases where they're browsing different web pages and we're grabbing them because of keywords on the web page or on a random sampling basis. In some of the Ethica studies out there, audio is being recorded from the phone. And there's also some information that Kurt put into place with IEPI earlier, but has continued on sort of what apps are being used over time. More than that, there's other sources of data that are often cross-linked to this. Scott, I think, has encountered in some of his consulting point-of-sale data, data on sales records from large chains, and we've worked with it in our group. You folks may not be aware, but Garrett Hansen and Stephanie Dilsner last year did a very nice little 394 report looking at point-of-sale data on mosquito-related projects and how that correlated with mosquito numbers in Saskatoon and how it correlated with temperature and things like that. So point-of-sale data is a big interest out there in big data. It's kind of bread and butter of a lot of data science initiatives now in corporate sphere, but it's also of interest in the health sphere. What people are buying, what pharmaceuticals, what sort of self-care devices, et cetera, how frequently are they filling their prescription? These are all really important things, okay? Administrative data is large-scale data like we get from ministry partners, Ministry of Justice, Ministry of Health, that often is voluminous as well. And then environmental sensor data is increasingly key as well. Our buildings are robots around us, and they're collecting massive amounts of data while we sit here in order to regulate the temperature. And increasingly we can leverage that data for health insight by tapping into those data systems. And organizations do in order to deal with problems in their buildings or to save energy or what have you. And finally, it's this big area that we're just now starting to get into. And over the next year, I expect for our group, this is going to be a sizable area of expansion, looking at how people use social media and their use on Twitter, Facebook, posting things to Snapchat or what have you, using that to gain some additional insight. And all this stuff has to be linked together. So volume is very large. Sometimes we'll have dozens of megabytes per person per day. Often we might have 10 times that. And as I've noted, the volume of data often requires different handling techniques than for traditional systems, for storage, for analysis, for visualization, etc. And if you've worked with the Ethica system, you'll know, logging in, you can see some indications of the volume of data. This is for Iden's, one of Iden's studies, right? This is the group 2 of that study, and this was done, I think, in March, and at that time we had something like 58 million linear accelerometer records, from across the participants, and a comparable number of orientation records, gravity sensors, millions of GPS records, etc. This data is also coming in at very high velocity, so for a given person, we'll have massive number of data points for their behavior over time with respect to these components. Things like their Facebook updates, Twitter, app use, their responses to surveys, etc. All right? And some of the data sources, like the administrative data, have a lot less frequent updates, but you still might have many, many records on a given person. And, in the Ethica context, the big data and health context, variety is a pronounced feature, as it is for many types of data science issues in general. So this information is crossing by participant and by the time, and in SQL data sources, we end up doing joins to link it together. So Jin Tong, who was at yesterday's meeting, some of you know her, she pre-aggregates tables joined by dozens of rows so that we can try to query them over time. Okay, let's talk some about the implications of this and what does this have to do with scalability. Well, we have huge amounts of data, and it's only going to grow, ladies and gentlemen. We're going to have larger studies. Alberta has talked about running studies of 100,000 or 200,000 people with Alberta, with our Ethica system through Alberta Health Services, and keeping those systems running for decades. So we're talking about very large amounts of data here, and we are quickly outgrowing our britches with the SQL systems we have right now. Even now, the queries are really slow, and this is generally indicative of the need to have the ability to take our analysis tools and scale them in the sense of allowing them to handle much, much larger, in this case, volumes and variety of data than they currently can. We need scalability, though, in a couple senses here. Firstly, we have to deal with large amounts of data, and we have limited resources. The limited resources, two of them stand out immediately in my mind, memory and CPU speed, although time is in there as well. We don't want our analyses to take forever because of the exploratory nature of them. So, we can very easily exhaust memory on a server. There's in some of my software engineering courses, we impart first an understanding of the principles of building programs and good effective software engineering techniques, and then at some point I need to help students understand that not real-world software engineering in many contexts is not merely a matter of building those programs in a pristinely structured fashion. You need to take into account the nature of the load, the nature of the requests, the nature of the data that you're dealing with, in order to have a system that will scale effectively. And when we're dealing with web-based clients, we may be dealing with bursts of data access where you have 100,000 people accessing your website. And that's a good thing, and that's not something that you want when you want your system to fail. You want to shine when people are most interested in it. And so it is here with scalability, except that where I can go for a couple of years without telling my undergrad students about the birds and the bees associated with effective scalability and needing to think seriously about performance issues, needing to worry about transactionality in the context of large-scale concurrent use in a way that grapples with the performance. Here, we have to deal with those issues up front. That's what data science is about, is dealing with these large amounts of data. And we can very quickly exhaust memory. It almost can be... It can be done super easily without even noticing it. Naively undertaking queries in a data science context often leads to non-starters as far as performance is concerned. It ain't going to work because it's just too slow. Or you're going to be doing exploratory work with the data, and it ends up taking 50 times longer than you hoped, and it really gets in the way of your learning. So memory is one of the key resources. Our machines have limited memory. So what? If we look around the table, we might have different machines, 16 gig, 32 gig maybe, if someone has a really loaded machine. We can fill that up within seconds by reading from data sources. Yes?
In fact, one of the reasons we had this issue is that this is a 32 gig machine right here, and for projects, the project I actually presented during the boot camp, they handed us data that we ended up not using, except for in very summarized form, because one state of the United States, 150 states, it's not a very large state, that data for a year of point of sale data was 50 gigabytes.
Yeah.
And we had nothing that could actually read it into memory to actually even look at it. So R was the only thing that could actually even put it all in RAM. Like Excel choked, of course, we didn't even bother using that, but other data analysis packages literally could not handle the amount of data. And this was just by the way, it was a 50 gigabyte text file. It was like literally a report dump from a database. So yeah.
Yeah. So
and that's small from data science concerns.
That's right. So memory is a huge issue. I think we're cracking in the Ethica context. We can readily crack a terabyte of data for a study, and so we're talking about something where it's a non-starter to just naively pursue it in terms of memory or to use purely traditional tools. Secondly, is CPU speed. It used to be that CPU speed was observing the speed was observing Moore's law in the sense that it would double every so many months and so on. We're far from that time now. We're hitting quantum limits as far as the size of features on a device, and we are also just not seeing the performance rises. With a single processor, single core, we're just not seeing the performance rises we traditionally have. So we cannot expect that somehow we'll just sit back and with the latest generation of Intel chips or something, it's going to allow us to process the next generation of data. It ain't going to work. It just is not going to work. We instead are increasingly needing to use parallel processing in a big way. We scale out rather than scaling up. We're not trying to just double our processor time. And you could throw a lot of money at it and not get a huge speed up processor-wise, not get orders of magnitude. Instead, what we do, if we want to be intelligent about processing this data, we farm it out. We make it accessible to many processing units, many servers or many cores on a given server or GPUs to allow them to process it. And that doesn't come for free. We need techniques that will let us do that transparently without tying us up all the details, getting in the way of our thinking about the data science, about the sort of analytics, tie us up with thinking about the plumbing only. And that's a risk. So we need to exploit these opportunities from speed that come from using many computational resources rather than just rather than sort of trying to have more. This should actually say, it shouldn't say additional processing, rather than speeding up our processors directly. We're not going to be able to go out and buy a more expensive computer that supports this down in the computer store. Another issue that comes up a lot in data science is dealing with exceptional conditions. This is, for software engineers, one of those things that's kind of a point of maturity when in your undergraduate career you realize that you can't just deal with the typical case or the hoped for case when you're doing calculations. You need to deal maturely with problems that come up. And in data science, these problems are of three very prominent types that I've listed there. There may be more that could be put down. One of them is we have missing values. We have cases where GPS wasn't measured for a time. We have cases where, this phone lacks, a working accelerometer. We have cases where there's sporadic problems with a sensor, or because of battery exhaustion, it cuts off certain sensors for a certain time. We got to deal with missing values. Missing values are extremely common. And, in R, they could be indicated with NAs, right? And one of the strengths of R as a platform is that it has a lot of mechanisms that can allow us to somewhat more gracefully deal with NAs. But R is just not going to cut it for very large-scale data, unfortunately. It's a wonderful platform. I love it to death. But for the types of data we're talking about here, it would get really bogged down at many points. So that's one sort. We need to be able to handle these missing values well. Secondly, we need to be able to handle failure across machines. If we're using this whole cluster as Winchell is want, if we're doing BOINC or whatever, we need to be prepared for the fact that machines go down. They shut down the machines for an exam, right? A machine fails because of a fan problem. Someone comes in and reboots a machine. This happened to Narges, I think, at one point. Machines fail, and we don't want the failure of a machine over in Spinks to throw our entire analysis into disarray. David Gifford, the professor at MIT, who was a young chap when I was there as a graduate student, commented once that it's great that the world is interconnected via computer networks, but what you don't want that to be is if someone trips over a cord, in one building, that it stop software from working all across the world. I mean, that way lies madness. Much of what we do in software engineering is helping ensure robustness in the context of problems. Much of what we do in computer science these days is about ensuring that we can build robust systems that can take advantage of the interconnected world but are not vulnerable to it in new ways. And so this issue of failure across machines is a big one. We also get error conditions. I mean, I think everyone here has gone through that at one point, right? We have a divide by zero error or something like that comes up. We have a minus infinity value that sneaks in there, and we end up getting a result. And we need computations that can handle these things but still give us value. We don't want just the occurrence of one NA to mean we don't get a result back from our computation. We'd like to get a result back that lets us know about the problem but doesn't stop it in its tracks. Okay, and then finally, in data science, we want scalability also from the point of view of going from very exploratory data analysis, where it's back and forth interactively, you can see visualization immediately, you go modify something, you see a new visualization, all the way up to, so very sort of scripting-like work, all the way up to situations where we have large-scale code bases that are robust, that have well-tested libraries, that have been validated, and that we use on a regular basis as core building blocks of our computations. Now, why Scala? So these are some needs of data science that point us to scalability. If we're doing data science and we're not thinking about scalability, we're missing the boat a lot of ways. We will end up not making progress. We'll end up just treading water, dealing with slow response. It will get in the way of our learning, which is at the heart of data science. So why Scala? Why do we talk about Scala here? Well, there's a number of reasons. It secures a lot of benefits that reflect the fact that it's and we'll talk a lot more about Scala, but it's a language that supports hybrids of functional programming and object-oriented programming in particular. And the functional component is very attractive for software engineering. It turns out it's also very, very attractive. It's also compelling for data science. That's why we're talking about this book in the context of data science. Because, ladies and gentlemen, functional programming is not only heart-achingly beautiful, it is also extremely performant when we're dealing with these sort of scalability challenges. So we'll talk about that. Why? I want you to grok it. I want you to really understand it inside out, because a lot of things that just seem like curious sides of functional programming languages turn out to be really, really important for scalability. And there are factors that are often lacking in other languages that we love and cherish, like Java.
Is that why the name's Scala?
I actually don't know the origin of that term. You could probably find it in seconds.
It's good at scaling.
It may be. I've mused about that as a possibility.
Without direction. It's not a vector.
It's not a scale, it's a scalar.
Okay. I like this being interactive. This is good. I appreciate Scott and yours and Winchell's comments. Everyone can jump in.
Portmanteau of scalable language.
Sorry?
It's a portmanteau of scalable language.
Nice. Scalable language. Okay.
Yep.
Now, there's some key data science needs that are supported, and many of these are via functional programming, but I wanted to list them because I actually want you to leave this course grokking these, okay? First of all, we have limited memory, as I said. We need to deal with our limited memory. We could just trivially fill up our memory. Boom, dead. We're not going to be able to make progress. What this means at a concrete level is we want to avoid taking, as we process successive steps of our computation, needing to bring all the data into memory and keep on making sort of changes to it, the whole data set in memory, or make new copies that are sort of have updates in various forms, and that are the transformed results of it, and keeping that in memory. If we do that, we're dead in the water, because our memory will fill up very quickly. If we have to keep the whole data set in memory, or if we have to keep transformations of it as we process it, cleaning of it, where we knock out certain data, summaries of it, etc., that's going to kill us memory-wise. It's going to kill us if we try to keep these things in memory. And so it turns out the key, an absolutely key thing to prevent this from being a problem, is laziness. Now, we're going to talk about laziness, what laziness means, but basically it's a type of non-strict computation. What does that mean? Well, what it means is when you characterize a computation, I say, I want to compute this like this. It actually doesn't perform the computation immediately. It doesn't perform it until it's needed, ladies and gentlemen, until it's actually required, until you need to put it to use. And that may seem like a kind of curious, nice feature. After all, we can defer things. Maybe they'll never be needed. It prevents speculative sort of computation. But it's more than that. It actually allows us to pipeline operations. It actually allows us to perform an operation in a way that doesn't load all the data in. Instead, allows us to process each data item one at a time instead of loading the whole data set in. This is really important, and we'll see why this is. Second of all, we want to use many processors. Well, it turns out Scala has beautiful mechanisms for performing parallel computation using parallel data structures and things called higher order functions that we'll be using a lot. It turns out that the types of computations we can characterize in Scala can often be beautifully just mapped out over computing units, such as cores in your computer, but also with futures, for example, and with actor-based frameworks like Akka, and then with mechanisms that are built into Spark, like resilient datasets, RDDs. We can actually transparently map our computations out across many computers, many distinct computers, okay? Another feature, which really I should have in here, is the fact that we can knock data out of memory because we don't have to keep it around. Why? Because we're using functional description and we can recompute it at any time. So we can trade off recomputation with keeping it in memory. I should really put that in there. Laziness, recomputation. This is absolutely key to the Spark idea. Oh man, okay, I'm gonna save this thing in case bad things happen. I want this to be fault tolerant. Okay, boom, there we go. Okay, so it turns out that Scala supports very nicely as a functional language the ability to recompute things easily instead of storing them. So you can either store them on disk, store them in memory, or you can recompute them. Okay. It has a beautiful capacity to robustly handle exceptional conditions, even in parallel code, where it's key. You farm things out across this whole machine, and not only are the dependencies clear, which will allow for farming it out easily, but if there's a problem, as there will often be somewhere, you get back results in a way that you can still utilize the good ones, but know about the bad ones and work to remediate them as necessary. Now, in the case of something like Spark, it actually hides errors from you across a cluster. It actually hides the errors. It actually, if a machine goes down, it will let you seamlessly continue on. And that's nice, but that's partly because it is built atop of Spark, okay? Atop of Scala, thank you. Spark is built atop of Scala. Scala is also scalable from sort of exploratory work to large-scale rigor, okay? To very, very rigorously defined, type-checked, and reasoned about large-scale programs. And at the same time, it can handle, in a very flexible way, sort of the type of interactive changes to our data pipeline we want for computing, for our analysis. We can change how we analyze things in a very, very flexible fashion, okay? It has a rich type system, which is statically typed. What this means is that and I think something has gone off at the end now. Okay, it's statically typed, meaning a lot of errors that would be slip through the cracks with Python and bite you at so-called runtime. When you're running an analysis, they can be caught up front. It will tell you, this program is nonsensical, go fix it.
This is Java too, right?
Java does as well, yeah, exactly. It's statically typed. It's meaning that it's typed in a way that when you're dealing with quantities, variables, values, and so on, it knows what type they are. The good thing with Scala, the beautiful thing with Scala, is that it infers a lot of that automatically. So you don't have to specify it explicitly. In Java, you actually have to be very specific about it. In Scala, you have to tell it some of them, and it can figure out the others, which is a thing of beauty.
So are you saying like you don't have to cast things as much in Scala?
It's not so much casting, it's that you don't have to do type annotations. We'll see soon enough, okay? You don't explicitly have to declare things as being of this type or that type. It will figure out what it is, what it has to be given your definitions.
So if you give an initial value of a number, it knows it's a number?
Yes.
Okay.
Yeah, and other things, sure. And it's a compiled language. It's quite performant. Compared to something like Python, it is just incomparably more performant in terms of its actual performance in inner loops and so on. Now, if both of them are calling off to things written in other languages, that won't matter as much. But we can write things from the small scale to the large scale in Scala in a way you couldn't with Python. Python is going to have some real issues. Python does not have rigorous type checking. It has what's called duck typing, and it is enforced at runtime. And often what it leads to scripts and scripting languages like Python, they die from obvious errors that could have been caught in a rigorously checked language. Okay, so why functional programming? Why are we going to be spending time going through these chapters here? Why going through these chapters? Well, it's for a number of reasons. Equational reasoning, we can sort of reason about the meaning of a program in a very clear way that's not obvious, that when we're dealing with code that has lots of side effects, that has lots of updates to the state of the program going on, it gets in the way of our reasoning. We have to sort of trace down dependencies in really awkward ways. So equational reasoning, it's like reasoning about a mathematical equation, like an algebra, how you can just substitute, x equals y plus z, and a equals x plus y, and therefore we can sort of just substitute in, x is y plus z, we'll substitute it in that later definition. We could just reason through it in a transparent fashion. Second thing is we can compose very simple mechanisms to yield really powerful results, really insightful results using very simple little elements just composed in orthogonal ways. It's beautiful. It's also very modular. We can sort of break things up into pieces and use them to sort of characterize different elements of the system in a way that they're quite independent. We can handle errors much more easily. It turns out what Scala rides atop is a functional way of handling errors, and it's beautiful. And it puts exception handling to shame. Exception handling looks awkward and quite limited and quite obscure compared to what we can do with functional languages. Your clear dependencies. You could see what depends on what much more easily than in languages that you may be familiar with in the C family, for example. Languages which involve updates to state very readily. And this is key for parallelization. You can see the dependencies very directly, and therefore you can take advantage of the program. We'll see a lot of these in more specific terms. You could specify asynchronous operations really easy. You could say, hey, look, I want to go off and read this web page, and when it's done, process it like that. And when that's done, process it in this way that's looking up definitions of words and dictionaries and so on. After that's done, handle it in this way. After that's done, it's just go figure, go off and do it. And whenever the data comes in, it will process it, and you're not just waiting for the data. It can handle it asynchronously. In other words, when the data comes in, it will handle it. Until then, it will wait, and it may exhibit some timeouts. Sending code to different machines is minimal trouble. That's easier on a functional context. And immutability rules out many errors. Okay, so functional programming is the key to Scala's strength. Now, we have limited time left here, but I would like to use it to explore Scala a little bit. Okay, so I would like you to go call up a Scala console. Now, if you don't have a Scala console, pull up to someone who does have one. Okay, and we will engage in Scalaizing here. Okay, so here we go, and I'll make this a full screen. So, ladies and gentlemen, might as well do it now. For those who have access to the Moodle site for the course, I have posted, let me go see if I have this around easily, but I have posted in the site for the course under the data examples area, or example data, I have put in a, okay, so let's go put this there. I have put in a thing for download, which is called document.txt. Okay, document.txt. It's under the examples area. I want to make sure it's fully visible. Yeah.
I don't have access to it on Moodle. The class.
Oh, you don't?
I don't see the class at all.
Okay, so for some reason it's not associated with you. Okay, so the easiest thing for me to do will be to email it to you.
So oh, here it is. Okay, it's under my courses, but it's not on the list.
It's under my courses.
I got it.
Yeah. Yeah.
I'm still learning how to use Moodle.
And I have registered for the course, but it needs the departmental
approval.
Yeah.
Absolutely. So send mail to Gwen, and she'll give you approval.
Oh, okay.
Yeah. You could say you spoke with me.
So by I don't have access to the course. Like.
Okay. So what I can do is send this file to everyone right now. Okay. So I'll send it to people via email. Okay. Here we go. And let's go drag this over here. Okay, and we will send it to, okay, actually we need to send it to the same group to whom I sent things earlier. Okay, here we are.
A few people are not on that list, including Winchell.
Oh my gosh. Okay. Adding insult to injury. Okay, that's really ugly. Okay, who else is not on that list? The people who are not on the list may not be here.
Arash wasn't on the list like you said last night.
Okay. Tina
and Arash asked me why they are not on the list.
They should be in the list. It's they weren't in the sign up for the course. I mean, they weren't in the doodle poll. And I think maybe they were admitted for the doodle poll list, or maybe they didn't fill it out. I don't know. But in any case, I need to get them invited. By all means, Tina is welcome. Okay, so let's go go there, and okay, so we want this guy, and here's the data, and there's a thing called document.txt, okay? And I will send it to you. So this is example data, okay? Arash. Yes.
I'm not here.
You're not here as well. Okay. How? Okay. Okay.
These people are left.
Example. Example data. Okay. So that's been sent to you. You can download that to a folder, and you should start Scala from that folder. Okay. We'll probably be actually using it more next time, but you can put that there. In the meantime, I'm going to switch over to my Scala console. Now, one of the very nice features, I consider a very nice feature about Scala, is that it's a compiled language, means that it takes your description and puts it into a very efficient so-called bytecode. But it does so in a way that still allows for interactive exploration. And there's this thing called the Scala shell, which basically allows you to interactively make use of Scala. And there's a similar one, the Spark shell, that allows you to use Scala with Spark, etc. Okay?
That's a format issue.
Well, yeah, it's not meant for you to open. That's what the raw data is. Yeah. Okay, so ladies and gentlemen, yes.
I mean, it's just a text file, right?
It's a text file.
A thesis submitted to college and so on.
That's exactly right.
Okay.
Yeah.
I find that amusing.
Yeah. So I wanted a big text file. I actually I sometimes prefer this example, doing it on Linux and Macs, but for those who had Windows, I figure, okay, I can't rely on that. Having a dictionary of words available and user-dict words, so I figured I'd just send you a file.
How about Google Drive?
Yeah, I could put it on Google Drive. It's a good idea, but I'd prefer not to set up a parallel site for the course when we have Moodle. I prefer to do things through Moodle if possible. Okay, ladies and gentlemen, so I put that file at a certain place, and I want to start Scala from that same place. Okay, so I went to the place where the file lives, and CD'd to it, right? And I want to do Scala from there. Okay, Scala, boom. Okay, now, ladies and gentlemen, the adventure begins. Okay, okay. So let's put in place a few sort of basics here. What we're going to do is I'm going to use this time to illustrate a little bit some features of Scala. I recognize that this, like the first day of my boot camp or the first presentation, is going to be a buzzing, blooming confusion. You're not going to know what this is, but you're going to see some interesting features of it, which when I go systematically through the Scala language may give you a concrete point of reference. This may also help motivate you to some of the features of what we can achieve in Scala so that you feel more invested in learning more. Okay, so this is what I'm going to do. I am going to say val. So in Scala, we distinguish between variables and values. In Java, if we want to keep around a value, often we just declare it as a variable, right? We declare a variable for it, and maybe it's a const variable, but it's a variable, but it doesn't vary. And so in Scala, most of the things that you're going to be using are actually vals. You don't need to overwrite them. A variable is associated with some a storage location that can get overridden over time, and that exists in Scala as well. But a val is a name for a value. Okay, it doesn't have to be allocated memory. It doesn't have to be given a place because it's never changed. It's never updated. Okay, so val, and this is going to be called vector random. I'm just going to try to use a name that that'll be fairly obvious. And what I'm going to do here is say I'm going to create a vector of random numbers, okay? So I'm going to say vector.fill, and I'm going to give a certain number of elements. I'm going to say 200,000, okay? Dot, okay, so I'm going to fill it up with what? Scala.util.random dot next double, okay? So this is a little formula. It's actually what's called a by name parameter. This gives an expression that for each element of this vector, of these 200,000 elements in this vector, this will be evaluated.
Don't you need a dot after the 200,000 there?
No, I don't. No,
Oh, okay.
no. It's a curried function, which means that it is first provided with this. This returns a function that is then provided this as an argument.
Oh, that's interesting.
Yes, it's a fun, beautiful thing.
Vector.fill is a curried function.
Sorry?
Vector.fill is a curried function.
Correct. It's a curried function. It takes
So
two types of
you're
arguments.
literally giving this
Yes.
about this is the parameter for this function, and this function returns a function for
Correct.
which this is the parameter.
Yes. Yeah.
That's pretty cool.
And they're actually, you don't even have to declare them as the same function. Well, I'll show you. Since I'd like this to be, we'll show how to define a function like that.
Sorry,
Okay.
this is very interesting.
Okay. Here we go. So I'm going to say vector random. Boom. And it's going to go off, and it's probably paging in my thing here. Okay. So here's a vector.
I got an error.
Okay. So what error did you get?
Not found value scale, and it's pointing to the right.
Scala.
Yeah. It's pointing to the S in Scala, right there. I don't-
Scala or scale?
I must mistyped it. Okay, my bad. Sorry, this is really small print, so.
Yeah, it's Scala.
Well, I figured.
Scala.
Okay, got it.
Okay.
Sorry about
Okay,
that.
so ladies and gentlemen, I'd like you now, having done that, to do some basic things. We're going to say vector random. Yeah.
You can't really see the
Okay. Give me a sec. I'll just move it up. Okay. So one thing we could do is we could say, okay, compute the sum of it, right? Vector random dot sum. So this created a vector. This created a vector of successive elements, right? These are the elements shown for the first bunch of them. Boom, boom, boom. These are random elements between 0 and 1. Okay? And now we're saying, okay, sum up that vector, right? That's one thing we could do, okay? Another thing that we could do, we could say, let's map that vector. Let's apply a function to each element of the vector in turn. So we could say, let's square each element of the vector, okay? So I can write this in several ways in Scala, okay?
You still can't see it.
Sorry? Oh, you still can't? Okay.
Window up is
So
the-
let me just make it smaller.
Yeah, that works.
Okay, cool. Okay. Vector to map. Can you see that?
Yeah.
Okay. So this is a vector, and we're going to say over each element of the vector, in turn, we're going to say how should it be transformed. In other words, we're going to, for each element of that vector, we're going to apply a function to it, and we're going to get back a new vector. Okay. This, you notice that this is an immutable vector. What that means is that it's going to, when we transform it, it's going to return a new vector, okay? Now you may think, how could that possibly be memory conserving? Well, the key thing is it allows sharing of data structures, because they don't get updated. You can have multiple things sharing them. No one has to worry that the others will update it in a way that will change it out from under them. It turns out immutability helps save memory, which is an unintuitive thing. So here's map, and we're going to say for each double, we're going to call it D. I want to square that double, okay? For each double, I'm going to give this a function. Map takes a function in. The vector of random, we're saying, hey, apply a function to each element of this vector and get back a new vector. What is this function? It's going to take in a double, and then it's going to multiply that double by itself. Okay? like that. Do you see that?
Right.
Okay, and I'm going to say, okay, and it's going to give me a new thing, which is a new vector. And if you look at each element of the vector, here's the first element of this one. The first element of this new one is the square of that, it turns out. Here's 0.9, and this one's 0.83, okay? So we got back a new vector that's the square of that. Okay, let's do something more, though. Let's ask, okay, what's the sum of this? Well, this guy is returning a vector, ladies and gentlemen, so we can say dot sum there, and it will sum up that vector. This is the new vector. You notice that this new vector, the sum of it is actually less than the sum of the old one.
Which is correct.
Which is correct, because each number is between 0 and 1. So in almost all cases, except for 1 itself and 0, its squares can be smaller than it. Okay? So here we got the sum. Do you see that?
Yeah.
Okay. So that's all well and good, but we're going to do something more. We're gonna say, okay, count how many elements are in the vector. Oops. Okay. Or we're gonna say size. Sorry, not count. Size. 200,000. No surprise there. Okay. We can ask for its size. We could ask for its sum. We could ask for its size. Do you see that? Okay. Next, let's do something different. Let's say we want to now filter it, this mapped value, to get all values which exceed 0.5. Okay? Oops, d greater than 0.5. So, to be clear,
We can
here's...
use again d.
Yes, we can use
number.
d. Yep. D is only known within this function. So we could use d.
We haven't
Oops.
declared a single data type yet. Well, except for vector random, I guess.
Yeah.
But not even that.
Yeah, but that was Scott deduced from
That's
our
okay.
arguments.
All the data types so far we've
Exactly.
inferred.
Okay, so what I was saying is we could filter this. We're going to take in, what is this filter going to do? To do its job, it needs some information. What information is it going to do its job? Well, it's going to be applying a function to a vector. What's the function it's going to apply? The function is going to determine for each vector, or for each element of the vector, whether or not it should be filtered out or should be retained. We're going to give it a function that's going to say whether or not it should be retained.
Right.
So the function that we give it is, we ask, okay, is this value greater than 0.5? Okay? Greater than 0.5. If so, we're going to retain it. Okay? Now, so here we go. And here we get back a vector. Ladies and gentlemen, how would we ask what the size is? How many elements there are in that vector?
Can't we just append dot size?
We can just do dot size at the end, right? Boom.
And this is basically pipelining things?
Yes. Yeah, but this one is not going to be pipelining it incrementally. We'll do that in a minute,
Oh,
okay?
sure, no, I'm just looking
Okay.
at this. That's interesting.
Okay, so this one, what is it doing? It actually starts with a vector. In this case, it's going to transform the vector to become a new vector. And that's actually calculated the full new vector here. And then it's filtering that new vector, it's filtering that squared vector to be, with each element squared, it's filtering it down to only retain those elements which are greater than 0.5 in it, and then we're calculating the size of it. And at each of these points, we have a whole new vector, sort of, after this map, this one where we're squaring each element of it, we have a new vector computed. After this filter, we have a new vector computed, and then we're taking the size.
But what we could do, we could filter vector random first so that we only have
Yes.
to square the items that...
Correct? Absolutely.
Filter.
Absolutely. Yes, we could change the order here. These are modular operations. Okay, now, yes.
So what is size? I forgot.
Size is just reporting the how many elements there are in the vector,
Oh, okay.
how many things are in the vector. Okay, now, ladies and gentlemen, let's do the following. I would like to actually have this be done incrementally, okay? Incrementally in the sense that rather than computing a whole new sort of vector structure along the way, it'll be done each element at a time. So it only needs to be considering it, okay, for the first element, okay, what is its square, and is it in the filter, etc. The second element, it'll be doing it incrementally. How do we do that? Well, you just say .view.map, and that will make it a lazy collection, okay? And you can see that here, it doesn't change the number, but what changes is that it's actually pipelining these, so it's performing this for the first element and then performing this for the first element and then going on doing it for the second element. So after the map, you don't have a whole new data structure. What you're actually doing is transforming you're actually doing calculations on each element of vector random without creating a whole new data structure. But let's continue to look at this. Let's do something a little bit more with this, okay? So we just transformed it to be lazy and to be done incrementally. Let's do something more with this though. I would like to do the following. I would like to go and here apply a grouping operator that will compute compute how many of these fall within different categories, okay? Different size categories. Something like a histogram, okay? Okay, so rather than computing the number that are greater than 0.5, I'm going to go back, I'm going to get rid of filter because we don't need to do it that way. And I'm going to say group by, okay? Group by, and what we're going to group by is the following. We're going to group by, so group by takes in a function that's going to say, it takes in a function which is going to be applied to each element in turn, and for that element, this function is going to tell what group is this in. What group is this one in? So what we're going to tell it is basically only pay attention to the first digit. 0.1, 0.2, 0.3, okay? So we're going to put it into some categories. So group by here, and we are going to say, we're going to group by math.round of d divided by, d is standing for double here, 10.0, times 10.0 divided by 10.0, okay? So this is what you're going to be doing.
You're missing a bracket.
I don't think so. No, I got match brackets. Okay, and then so what this is going to do is it's going to actually go and for each element in this squared vector, it's going to determine which bin should it go in. And how is it going to determine that? Well, for that element, it's going to be using this to determine what bin it's in. Is it in the first bin, the second bin, the third bin? And it's going to do that based on the multiplication by 10, okay?
Is that a function that has to basically return an int?
Yeah, exactly. No, it doesn't have to return an int. It can return anything, a string or whatever category you want to use in your map to do it. And actually, we don't even, for clarity here, we don't even need this divided by 10. I'm sorry, we could even do it without it. We could just do it like this. To be clear here, what's going to be going on, just so we could see it here, you don't have to do this, but I'll show it to you, is we're going to have something like the group by is going to yield for each element, it's going to be yielding something like this, right? 6.19, 3.95, etc. And actually, I don't. I could have just done a map, and it would be clear. Here we go. I'm going to multiply by each times 10. Okay, it's because it's not showing it as nicely because of the view here. That's fine. I could have asked it. This is what it will see when it's considering each element, and then it's going to group by that. In other words, it's going to determine the appropriate category for it based on this rounding. Okay, and Oh, I see. Okay. Right.
If you put a group by D
Yeah.
and D, then it would just create 100,000 groups.
That's correct. That's correct. Yes. Okay. So, ladies and gentlemen, this is what it would see when it multiplies it by 10. If we did here math.round on this, this is what it will see. Right? That's what it will see. For each element in the original collection, just as a reminder, the element of the original collections are these. And it's going to be basically multiplying them times 10 and then rounding them. So this guy corresponds to 1. This guy corresponds to 8. This guy corresponds to 2. It's going to be rounding it, okay? Now, maybe it will be a little bit nicer if we could do math.floor. I think there is a math.floor here. And now, we're going to be multiplying, sorry?
I still don't see where it's mapping it.
Yeah, so, okay, so, it's based on the square of it. I shouldn't have printed out vector random. I should have printed out vector random dot.
Oh, that makes more sense.
Map.
Yeah, the result of the map is what it's getting, because that's what the group by is seeing.
Okay, yeah. Now it's
Right? This guy goes to this guy, this guy goes to this guy, this guy goes to this guy. To be clear here, let's see what's going on. This one here, this computation yields what the vector we see here. And then for each of these elements in turn, it's multiplying it by 10 and taking the and rounding it, right? So this one corresponds to that, this one corresponds to that. This here is basically taking each one and turning it and multiplying it by 10, rounding it to the nearest integer, and using that then as the corresponding value. Okay, so now let's go back to the group by, and what we will do here is we'll say group by this, and then we will say, so what this gives us is for each value, 0, 5, 2, for each of these values, it associates it with all elements that have that value. It groups them by that. In other words, it collects together them, all those that have the value 6, okay?
Apparently it does it in a map.
Yeah, this is a map. This is a map, okay?
You've got the view going on there, which is why it shows differently.
Yeah,
Yes.
okay. I'll do it without the view, and it may be clear, okay? Here's a map. So 0 is associated with all of these guys here, right? All of these here. All of these guys got grouped into 0, and similarly for 1. But let's further process this. Let's count the number of these. So 0 was associated with all of these items. All these items in the squared vector got grouped into the category 0 by this group by. Why? Because they all had the same value of this function. Any function that has the value 0 coming out of this, any value in the squared vector that has this yield 0 is grouped here. Similarly for 1, similarly for 2, similarly for 3. So now let's count the number that are in each one of those. Let's find out how many. Ready? We're going to do map value. Okay. Map value here. And for the map value, we are going to basically map it to something where we just count the number of elements, okay? So this is going to be a group. It'll be in or call it group G. We're going to map it to g.size, the number of items in the group. Because remember, this group, so map here, the original vector was a vector. Map on that vector returned a vector as well, just with each element squared. Group by groups them into categories. All the categories that had 0, all the categories that had 1. And that group consisted of a vector of elements that that had that category associated with them, as determined by the value of this function. Finally, we're going to map those values by just taking the size of the category.
So each of the categories are the values of the.
Okay. Sorry. Map values. It should be. So,
Map values. Okay.
map values. Yeah. Here we go. Okay. There we go. So.
The result of the .group by,
Yeah.
it returns a map,
A map.
not a vector.
No, it's a map. It's a
And
because
the
it's
vector is a
it's-
one-to-many mapping.
well. To be clear, why is group by yields a map? Why is what's coming out of group by a map? Well, it's grouping things.
Sure.
For each value of the grouping function, that each distinct value, it groups all the elements that came into it which had that value. So that's why it yields a map. It's a map from group to the things that had that group. In other words, they shared the same value of this function.
But it's a one-to-many mapping. Each index.
Yes, can have more than one, yeah.
Zero maps to many things.
Yes, correct. And it did, right? All of these items mapped to 0. Okay, so here, what are these counts representing? In intuitive terms, what does this count represent?
The frequencies of the bins.
Okay, the frequencies of what events? If we were to describe it in terms of the original vector, what do these represent?
The values of that vector which sits in the 0 bin and the
Okay.
count of them.
So that's getting close, but what are, is this a value of the vector? This is a count of vectors that are associated with this bin, right? Now, you'll notice that these bins are somewhat confusing because they're like 0, 5, 10. It's not so clear how they relate to the original ones. That's why we had this divided by 10.0. We actually want the labels for the bins to be, this is the bin starting at 0. This is the label starting at 3. This is the label starting at 1, etc. Okay? So this is listing, in short, how many values in the sort of squared, how many values within the vector produced by squaring each vector in the original vector fall within different categories, different range categories. So 44.9 thousand fall from 0 to 0.1, from 0.1 to 0.2, 33,107, from 0.2 to 0.3, 22,567, from 0.3 up to 0.4 is 18,000, and so on. And you notice all the way at the end, 0.9 to 1 has 10546 plus this one that it exactly the value exactly 1. Okay, on it. There were some at the end there. Okay, so this is grouping together elements here. That's quite nice. How would we do this in parallel? We saw earlier how we could do it incrementally to avoid, because every time it's building a new data structure, this is what we do to do it incrementally, ladies and gentlemen. Does the same computation, but without creating a full new data structure after this, without creating a full new data structure after this, without creating a full new one after this. It does it incrementally where possible. How could we do this in parallel?
Nate,
Yes.
it's 12 o'clock.
Yes, I'm going to stop now.
Okay, so I was just
Yeah.
wondering how much longer we're planning on going.
About 2 minutes.
Okay.
Yeah. To do it in parallel, this is what we would do. We'd do .par.map. Now that will actually create a parallel data structure, which just allows this to be mapped over your different cores. Okay? So we are creating a parallel data structure, and that will allow these computations involving each element of the original vector to be given off to different elements of your computer. So one core may be working on the first set of 50,000, the next one at the next set of 50,000, the next one at the next set, and the next one at the next set. This, in short, is all done in parallel. And you'll notice the difference. Do you see? This is a parallel map. That was a map. This is a data structure that was set up to be handled in parallel. And if we had gone back and we had gone and looked at this earlier and we had done vector random.par, what we would see is that this is actually a version of the original vector, but with, it ran out of memory. Okay. Fine, I'll just do take the first 10 of it or something like that and parallelize that. And this is a immutable parallel vector. So I ran out of memory there for reconstituting, and you could see how critical memory is. This is not something you want to take lightly, but this will parallelize the computation. And actually, it was performing, when we did this, it performed it over multiple cores of my computer, okay, which is handy. But you can see the basic structure is the same. Ladies and gentlemen, these are what we call higher order functions. These are functions that take functions as an argument or return a function. And we're going to be going through a set of them, including map, group by, filter, and in fact also reduce, which are higher order functions. But Scala is filled with higher order functions, okay? Absolutely filled with them. And you'll notice that what we did here is we did a calculation that's divided up in a modular fashion into a set of fairly orthogonal operations. We mapped it, we then grouped it according to a certain predicate, and then the resulting groups, we mapped their size and their value in a certain way according to the size, and that allowed us to complete the operation. So we can take a complex operation, divide it up into pieces performed using these so-called higher level operators, these things like map, group by, map values, etc., and use it to perform a computation in a modular fashion. You know, maybe we in the end will be interested in something different. Maybe we're interested in how cubing it would yield different results. We could just go in, edit it, and go in and make it a cube instead of a square. And we can run it now, and it will be performing the calculation and telling us the results there. Or, you know, we could have done the square root here, math.square root, modify this. We could have divided up the bins into different numbers of categories. That would be changing only elements here. So this will change it to 20 different categories. And I could divide it up like that. In short, we have a fairly orthogonal way of computing this, or what we could have done is done this. Instead of computing the size of each group, we could have computed the sum of each group, right? We compute the sum within that group. You know, what's the sum of the items within that group, rather than computing the size of that group. And here it's gone off and is computing it, and it will come back in a minute with the respective sums. Okay. So this is the kind of enterprise which we're going to be exploring, and these elements here, these map values, group by, map, etc. These things are sort of the bread and butter of parallel programming, of functional programming in Scala. These higher order functions together with reduce. But often we layer it atop of additional higher order functions that perform additional processing. Okay, so that's all for today. For next time, we are going to be going through the first two chapters of this book. Chapter 1, what is functional programming, and Chapter 2, getting started with functional programming. Okay, these are providing introductions to Scala from a functional programming perspective. We will also be going through next time elements of Scala to introduce you to the language. Okay, and this ran out of memory, so I'm going to be doing it instead with a with a view, I think, that may have a better chance of yielding staying within the memory. Anyway, that's all for today. Thank you very much, and we'll look forward to seeing you next time. You notice defining this using in a lazy fashion allowed the computation to complete in actually a very fast fashion here. So these, maintaining resources is important, and in Scala, doing so can be much easier than in many other languages and quite lightweight. Okay, you'll notice we didn't even have to specify the types for these elements, these Ds that we used. It figured out what the value of this group is here, what sort of thing it was. It figured out what this D was, that it must be a double. Figured out this is a vector of doubles. It can do a lot of inference for us, and that's one of the things that makes building programs in Scala more lightweight and more sort of simple in their appearance than with languages like Java, where you have to liter it with type declarations. Okay, thank you very much, and I will see if I can